Welcome to this class. Briefly, I will just go through what we discussed in the last class. We discussed about the field evaporation and how it is different from field ionization, and also we talked about post ionization effects, where the atoms which gets polarized at the tip surface, then if they get ionized and if they are there at the critical distance between the tip surface and the ionized ion, then they may that may happen, that post ionization will occur. It means that these ions, the electrons can be drained out of these ions again, and which leads to the post ionization phenomena. And this post ionization, it is nothing but similar to the imaging gas atoms which are get ionized near to the tip surface. Okay, so this is just similar to the gas atom ionization. Fine. So briefly I will go through it. We have last class we also discussed about in previous classes that the appearance of poles, and these are nothing but the projection or the stereographic projection of that particular element. For example, these are the poles. These are the poles which corresponds to pure aluminium. Pure aluminium. And these poles, you can see that there are, it's nothing but the low density regions, low density regions, and also we see that clearly these zone lines. Okay, so in today's class, I hope that we will cover this part, how these zone lines and the low density poles are observable during the field evaporation. Okay, so here this is a typically you can see that 1 bar 1 3 zone, and you can see the symmetry which is exactly similar to what we observe in the film. So these particular images are nothing but desorption images, field desorption images. Okay, I'll come to this terminology, and this is nothing but a 0 to 2 pole of pure aluminum FCC. This is a 002, and you can see this four-fold symmetry along this zone axis, or the 002 or 001. Fine. So we also discussed about the kingdom diagrams. Okay, so we talked about the charge states that are directly depends upon the induced electric field. Okay, and that is directly related to the curvature, the local curvature. Fine. And these charge states are the function of the electric field which is present near to the field, and these charge states, depending upon the element and the charge, they have a different field evaporation or evaporation field. Okay, depending upon the charge. So these kingdom diagrams, it is nothing but, you can see that in the x-axis this is the field. Okay, and this is the ratio of the charge, and you can see that these different colors corresponds to different charge states. Okay, I have given you an example of the effect of curvature on the atom map. Okay, and which is related to your charge state of that particular element. Okay, so we described in a aluminum magnesium silicon alloy, where there are magnesium silicon rich precipitates. Okay, and depending upon the charge states F1 and F2 of that particular ions, then you can get the tomogram with respect to that. Okay, so due to the difference in the charge states, locally the curvature or the electric field around that curvature will change, due to which the evolution of curvature, the evolution of tip in that particular location also will change. That will have a direct impact on the electric field, and due to this the electric field can reach evaporation field of one of the charge state like Mg2 plus or the aluminum 2 plus, that time these ions gets field evaporated. Okay, so this is a charge state for Mg2 plus. Okay, so that's why we see a different distribution of atoms even in the presence of precipitate. You can see that there is a concentration of aluminum 2 plus. Okay, so now coming to the instrumentation part. The APT instrumentation is very similar to FIM. Okay, so in the left side you can see a simplistic diagram, as a schematic diagram. Okay, so similar to FIM, there is an ultra high vacuum chamber which is having a 10 raised to power minus 8 pascals of pressure, and one of the important point is here, the sample stage can be moved in 3 dimension. So you have a X moment, Y moment and Z moment. Okay, so and in front of this particular stage, on the stage actually you can load several samples. Okay, and this movement of X direction, Y direction and Z, X and Y direction and Z direction, this movement allows that different tip surfaces to be positioned in front of the local electrode. This is a counter electrode. Okay, and here the temperature can go up to 20 Kelvin, and there is an application of very high DC voltage. Okay, and presence of this counter electrode, the counter electrode is also connected to a high voltage pulsar. We will come to this voltage pulsing, high voltage pulsar. Okay, and this counter electrode is nothing but a hollow copper foil, or hollow copper foil, and this hollow is having a diameter of 10 to 60 microns. Okay, and due to the presence of this counter electrode, if you have an atom probe tip needle in front of the counter electrode, the electric field lines will be highly concentrated, due to which your Kf, it means that field factor becomes or decreases. Fine. So this is the effect of counter electrode, which in modern atom probes these are regularly used. And specimen, as I told you, can be mounted on a substrate with the sharp needles, and on application of voltage pulse or HV pulse, these field evaporation of the atoms on the tip surface, they can get polarized and they can field evaporate, and these field lines will be concentrated into the electrode, hollow electrode, and these polarized atoms which are converted to ions, they will go inside along the field lines inside the electrode. Okay, they will follow this particular path. This HV pulsing, it will last around few nanoseconds. Okay, so pulsing means if you have a voltage, so HV pulsing means the voltage at a certain time, it goes up and it goes down, it goes up and it goes down. Okay, and the time interval between up and down, it can be the rise and decay time, it can be between 0.5 to 5 nanoseconds. Okay, so when your pulsing will be at the maximum point, you expect that the evaporation of the ions from the tip surface will be maximum. Okay, so we'll come to this discussion later, but for now these voltage pulses are of lasting for few nanoseconds. We can also apply, instead of HV pulsing, last class we have shown that there is another type of pulsing which is called thermal pulse, that is also called the laser pulsing. What is laser pulsing? You will apply the electric field. The electric field will be constant, but you will increase the tip temperature. Okay, so you will generate a beam or the laser beam or the light beam, laser beam onto the tip apex. So you can see these are the mirrors, and if your beam falls on, and by the using optical mirrors, this beam or the light or the laser beam is focused onto the tip surface. Okay, and the wavelength or the laser spot is actually much larger than the radii of the tip diameter, correct? And some of the photons, so the photons from the laser or the light is absorbed on the tip surface, due to which there will be an increase in the temperature of the tip. So due to increase in the temperature of the tip, then what will happen, it will assist the field evaporation of the atoms on the tip surface. Okay, so remember, in the laser pulsing, it generates pulses of few tens of nanoseconds. It can generate tens of nanoseconds down to hundreds of femtoseconds. What is femtosecond? You can say that 10 nanosecond is around 10 raised to power minus 9 nanoseconds. Femtosecond is 10 raised to power minus 15 of a second. Fine. So this is the difference. So we can actually generate a laser pulse or the thermal pulse which can last between the tens of nanoseconds to the down to the hundreds of femtoseconds. Okay, so this is in the right side. It's a different images. It's a different in different directions. So you can see that this is your atom probe needle. This is your counter electrode. Okay, and while applying the voltage pulse or the laser pulse, these ions gets traveled along the field lines, and this particular part is nothing but the detector. Okay, this detector consists of two parts. As I told you last time, these are MCP, multi-channel plates, plus there is a position sensitive detector, or we call as a delay line detectors. Delay line detectors. So our typical detector consists of these two important parts. Fine. So here there is an optical image. It's an optical or a camera image where you can see a very sharp needle in front of a local electrode, and this is a hollow electrode. Fine, around up to 60 microns of diameter. Okay, and back side of this electrode you will have a detector, which is schematically shown in the right side, in the upper right side of the diagram. Now we will talk about particle detection. So how these ions get detected by using this particular detector, which is composed of MCP and the delay line detectors. Fine. So now we will talk about particle detection. So particle detection, mainly we will talk about the ions, and these ions typically are collected by the detector. Okay, and this detector has two roles. One is the detector provides the timing and also the position. Timing means the time of flight or the timing, and the position means at which position the particular ion has hit or is impinged on the detector, position of the impact of each ion on the detector. Now, as I told you, this detector is composed of stacks of MCP plates plus delay line detectors, DLDs. And these MCP plates these MCP plates are in the chevron configuration. Chevron configuration. What is chevron configuration? You can see in this particular image. This is your cross section image. Okay, and you can see that this is this particular region is nothing but this particular region, and this is called a chevron configuration. Okay, this chevron configuration, it is composed of two microchannel plates which is arranged in at a certain degree, which is 8 to minus 8 degrees. Why this is being done? This is being done to increase the efficiency of the detection. So that, as in the last class we told that in the MCP plate is nothing but the periodic arrangement of the glass tubes. Okay, and these glass tubes are highly charged by the biased voltage, and when an ion hit to this glass tube surface, it generates a large amount of secondary electrons, and these electrons, when it is in the chevron, the MCP plates are in the chevron configuration, these electrons can again strike to the glass surface and generates thousands of electrons, or the cascade of electrons. These cascade of electrons will come out from the rear end of the MCP plate, and this, by application of a bias voltage between the between the delay cross delay line detector, or the fluorescent or the phosphor screen, and the rear end of the MCP, then these electrons will accelerate towards this particular delay line detector. Okay, so this is the chevron configuration is for effective ion electron conversion and signal amplification. Okay, and detection efficiency of a particular detector is between 55% to 65%. Why it is very low? Why it is not 100%? This is due to the, if you assume this particular glass tube, what will happen is, if you see the cross section, you will have a glass tube in like this, and this particular area, the electron cannot pass through it. Electron can pass only through the hollow area of the glass tube. So when an ion hits to this the non glass tube area, non-tube area, then what will happen? These the ions, when hit to the non-tube area of this particular area, it generates secondary electrons, but these secondary electrons cannot penetrate through the glass channels. Okay, so it gets reverted back. So ions strike the intra-channel. So this non-tube area is called intra-channel, or the web region, or we can call it as a web region. So these secondary electrons do not enter to the glass tube. So it will not pass through, and it will not be reached to the delay line detectors. So that's why the efficiency becomes 55 to 60%. But to improve the efficiency or the gain of MCP, usually what we do, what can be done is that this particular design of these glass tubes can be made as a flared entrance. What we see in the left side of the image, due to which it decreases the inter-channel region. Okay, due to which your probability of ion traveling through the glass tube will increase significantly. But so it goes up to 65%. Fine, and these ions gets strike to the glass surface, and converts to the large amount of secondary electrons. And also what you can do is one more technique to increase the detection efficiency is you can actually coat a layer of an MCP side by a conductive layer, coating by a conductive layer. Usually it is a nichrome. So what will end when and putting a mesh just ahead of the front end of the MCP. This mesh, and with the front end there is a negative biased voltage, and when an ion travels and it gets tied to the interchannular region, then what will happen? These ions or the secondary electrons which are generated by that strike, these electrons will go to the mesh, and due to this negative bias voltage it will reback to the glass tube channels. This is how you can reduce the loss of these electrons to the outside this MCP plates. So this is where you can actually increase the efficiency of the MCP or the MCP plates. Okay, so I hope now I understood that how these design of these MCP plates led to the higher efficiency of the detectability, higher efficiency of the detectability, or we can say that how we can generate large amount of cascade of electrons by multiple hits of these ions on the MCP plate. Okay, the next thing is, behind this MCP there is another detector which we called it as a delay line detectors, DLDs. In the start of the class I just told that DLDs gives the timing and also the position. Okay, so these delay line detectors are the particle detectors. These are the particle detectors that uses the time difference between arrival of any signal at different points on the delay line. Okay, and you can see that here this is in the right side, you can see a schematic diagram of this delay line detector. You can see these delay line detectors are nothing but a continuous wire, this blue color, continuous wire which is having a end point at x1 and another point at x2. So this is x2 point, this is x1 point. These are the two end points. Now similarly, this is the x position. Similarly for the y, this is the y endpoint, y1 endpoint, and this is the y2 endpoint. Okay, so you can see this delay line detector will be like this. Okay, so you will have a two x1 y1 and x2 y2. Fine, or we so this is the and these are nothing but a continuous delay line wires, conductive wires. Okay, so when the electrons coming from the MCP, the rear back end of the MCP, these electrons will hit to this mesh of x1 x2 and y1 y2. Okay, so what will happen? These electrons which is having a certain spread will generate the electrical pulse on those particular wires. Okay, so schematically, if you see that if you have a continuous wire, assume that this is a x1 position, this is a x2 position. When an electron cloud hits to the wire, conductive wire, so what will happen? It will generate a electric pulse on the conductive wire, and this electric pulse can travel in this particular direction, also in this particular direction. Fine. So you will have a one pulse, an electric pulse that can travel along towards x1 or towards x2, and measuring the time difference for the pulse to reach x1 and to reach x2, actually we can estimate, we can find out the hit position of that particular electron cloud. Fine. So this is how we can measure the xd, which is the position at which the electron an electron cloud hit to the delay line wire or the conductive wire. Fine. So okay. Okay. So now we'll talk about the delay line detectors. Okay. So as I told you, these are typically a particle detectors that we use the time difference of an electrical pulse between the while reaching the two positions x1 and x2, which is connected to the conductive wire. Okay. So this is used to determine the position of hit and also the timing. Okay. So if you see the stepwise of the function of this, the first will be the signal generation. Signal generation. So when a particle or the ion or electron or a photon strikes the detector, it generates a charge pulse. You can call it as a charge pulse or electrical pulse. The second is the signal which is generated has to propagate or has to travel. Okay. So signal propagates along the delay line. Typically this delay line is typically a conductive wire, and towards the two ends of that particular delay line, x1 x2 or y1 y2. Okay. Then third function of this delay line detector is the measurement of time. So that signal, as I told you, if there is an electron cloud, it hits to the delay line detector, it generates a pulse, and this pulse will travel towards x1 and y1, correct? And the signals at different points on the delay line at different times. Okay. So like this, an electron cloud which is arriving at this position after a certain time or at the same time, it is possible that an electron cloud is also arriving to the different position. Okay. To a different position at the same time, or it is possible that at different times these electron clouds E1, E2 and E3 can arrive at different positions of that particular delay wire, right? So depending upon the particle impact positions. So the time which is taking of that electrical pulse towards to reach x1 and x2 will depends upon where the particle has hit to the detector on that position. Fine. So how we can measure? So the fourth point is the fourth important function is it measures the position. It calculates the position. So this is by measuring the time difference between the signals that are arriving at different positions, different points, we can tell different points. Okay, with this you can the detector can detect the particle's position. So usually what we measure is if there is a delay line wire. If there is an x1, there is an x2. Okay, consider the total length of this delay line wire is Lx. Fine. So the position, if an electron cloud E1 hits to this position P1, then that position P1 can be calculated by the formula of xd. Xd is equals to Tx2 minus Tx1 divided by 2Tx whole to the power Lx. Okay, so here the Tx2 is the time to reach the end point x2. Similarly, Tx1 is the time to reach the end point x1. Okay, Tx is the total time along the line, and Lx, as I told you, it is the physical length of the wire. Okay, usually this particular okay, so I can write the formula again. So usually xd is equals to Tx2 minus Tx1 divided by 2Tx equal to Lx. Okay, so this is the position of the hit of that particular electron cloud on the wire, on the conducting wire. Correct. So this is the position calculation. The position calculation. The fifth function is to timing information. Okay, so these DLDs provides the timing information and can be used to determine the time of arrival of the particle. Time of arrival of the particle. Okay, so this is how it provides an excellent way of timing resolution and also the position of the hit of that particular electron cloud. So I talked about only in one direction xd. Similarly, you will have a yd. So you will have a two-dimensional position. So you will have a coordinate of xd and yd at the cross section. Correct. So this is how it is measured. DLDs are used for the measurement. So the timing information, the average time of flight can be given as Tx1 plus Tx2 plus Tx3 Ty1 plus Ty2 divided by 4. Okay, so this is the time which is measured. So there are two time pairs we can tell here, Tx1, Tx2, and there is another time pair Ty1, Ty2 for each of the XY line configuration. Okay, so schematically what we can see is we will have a mesh so you will have a x1, x2, similarly you have a y1, y2. Okay, so one of the drawback for these DLD detectors is multiple hit capacity. What does it mean? It means that there is a limitation which is imposed when when a different electron clouds or different electron or the ions arrive very close either by time or position. So it will identify as a same type of electron cloud or the ion. So this is imposed as a multiple hit related to the multiple hit capacity. So the total time of propagation of any signal along the lines, they imposed this particular constraint. okay, and to separate out the signals to each single ion, correct. And this particular phenomena which we call is a ion pileup, and usually most of the atom probes, this is the main detection limit for the capabilities, okay. And this particular phenomena can also said as if more than one ion hit is detected during a single pulse, okay. This also be termed as, this can be defined as if more than one ion is detected on a single pulse, correct. So this is the one of the drawback for the DLD detectors. So now we will come to another topic of what is the difference between field desorption microscopy and atom probe tomography. Okay, as the name suggests, it is related to the field desorption of a particular of a polarized ion from the tip surface that is directly detected on the fluorescent screen, correct. So before these MCP plates and also these position sensitive detectors came, usually the atom probe tomography was termed as field desorption microscopy. Okay, it means that whatever the polarized ion, due to the application of the DC voltage, those ions, those direct ions are actually hit to the fluorescent screen. So there is no position sensitive detectors. Fine. So it means there is no conversion of these ions to the electrons, secondary electrons, and be detected. But in the new atom probes, we usually convert these ions to the cascade of electrons that are then impinged to the these position sensitive detectors. So image is formed by the accumulating the ion impact positions on the detector. Okay, these images are also called desorption images. Desorption images. Okay, so desorption images, what are these called? These are the images formed by the field induced desorption of atoms from the specimen. Okay, so you can tell it as a desorption image or desorption map. Okay, so if you take a desorption image, if you compare an FIM and the desorption image, it looks very similar, but there is a difference in the electric field. There is a difference in the in the field ionization of these atoms when you use a gaseous imaging gases as or imaging ions, or when you use the dissolved atoms, dissolved ions. Okay, so they have a certain difference in the images. Okay, so the first image of field desorption image, the field desorption image was shown by Volko and Mueller in 1972. Okay, they called it as a FDM image. Then these FDM images, what Mueller student Dennis, whose name is Panitz, he has attached time of flight spectroscopy of these two FDM. So this was related to your atom probe. Okay, so this is the just a time scale. So we call it as a FIM, we call it as a FDM. FIM, you use the imaging gas, and these are get polarized or ionized at the ionization zone above the tip surface. Now, in FDM, this is not the case. In FDM, the surface atoms are ionized, okay, of the tip surface. Surface atoms of the tip are gets ionized, and due to the potential difference or the then and the voltage and electric field, these ionized surface atoms gets dissolved. That's why these are called field desorption images or the field desorption microscopy. So the trajectory of ions which are originating from the surface atoms of the tip will be slightly different from the trajectory of imaging gas ions, which are accelerated along the field lines from the ionization zone ahead of the tip surface. Okay, so there is a difference in the trajectory. So that's therefore there will be a difference in the projection parameters. Between the film and the FDM. Okay, so usually in film and FDM, if you see an image of a film image and of an FDM image, what we see is this is left side, this is a film image, in the right side it is a FDM image. Fine. So you can see that this is from the same material, tungsten, and you can see these concentric rings which corresponds to the atomic terraces in both the images. So this is a film and this is a in the right side it is a FDM, field desorption. If you see properly these concentric rings, the size of these concentric rings, you can see that in the FDM the size, the concentric ring diameter is lower than the film. Okay, so here the size of the concentric rings are larger in size. Here these are little bit smaller in size as compared to the FIM image. This is directly related, as I told you, the trajectory difference of ions which are projected from the tip surface. So in film, usually the imaging gas ions get ionized near to the ionization zone ahead of the that particular atomic terrace. But in case of the field desorption, the atoms which are actually attached to the lattice of the tip surface gets polarized, and these atoms gets field evaporated. Okay, so there is a difference in the trajectory of these contrast which we see on the detectors. Okay, so in the case of if you compare the if you compare these A and B for the FIM and FDM, you can see that. So in the case of difference between film and FDM, you can see that it is might possible that the contrast gets reversed. Means the concentric ring which is appearing bright can become dark. Why it is so? So this can be understood by the density, the atomic density which is projected on the film or the FDM image. Okay, the first case A is related to FIM, the second case is FDM. Okay, so this you can assume that. So first we will describe for the FIM. Assume there is a tip. And which has a local curvature. Again there is a local curvature. Fine. And Okay. Yeah. So assume there is a tip. Okay, and it has a local curvature. You can see, and you can see these atoms are arranged on the tip surface. Okay, and you can see there is a local curvature. So here the curvature is large, here the curvature is small, here again the curvature is large. Okay, and these are the gaseous atoms on the tip surface on the ionization zone. Now in film, the region of high curvature will appear bright. Okay, so the region of high curvature will appear bright, and because this is due to the directly related to the high density of hits on the film image. Okay, so you can see that the atomic density here, it is very high as compared to atomic density here. Fine. So these regions appears very bright due to the high density of hits on the film image. You can and remember that these gas atoms are just on the ionization zone ahead of this tip surface. Fine. And these gets polarized, and based on the distance like xc, which is if it is less than xc or more than xc, then these gas ions get polarized, and they can, depending upon the curvature, there will be high density of hits on the film image. So this particular region will appear bright, but this particular region will appear dark. But in FDM, the case is different. Here in FDM, assuming that this is a tip surface, okay, so there is a local curvature. So here there is a local curvature. So here there is a high curvature, here there is a high curvature. This high curvature leads to high electric field ahead of the curvature. Okay, so high electric field, and this induces a local magnification effects. What is these local magnification effects or the trajectory aberrations? These are when these atoms gets polarized or ionized. Actually, due to the local curvature and electric field, these particular ions gets repelled. Okay, so this repelled between the ions. Okay, so these local magnification effects is directly related to the repulse of the ions at that local curvature or of that higher curvature, due to which the electron density, so due to this local repel nature, these atoms will get lead to the trajectory aberrations, and this trajectory aberrations leads to a very low density just ahead of the curvature, but very high density at the terraces or the atomic terraces. Okay, so these will appear bright. Fine. So this is the difference between the FIM and FDM images. So using the data of APT, atom probe, actually we can replot these FDM images. Okay, so these FDM images are nothing but a desorption images, and these desorption images, wherever there is a low density, wherever the low density of atoms which are those appears dark, Okay, wherever the high density of these regions are there appears bright. So there is a difference in the appearance of desorption images and the FIM images. Okay, usually these low density regions are usually related to the poles and zone lines. Okay, this is due to the directly to the trajectory aberrations. As I told you in previous classes, the electric field around the tip surface is also directly related to the crystallographic axis, whether it is a 100, 110 or 112. Okay? Depending upon this, you will evolve to a trajectory aberrations which are related to the appearance of low density regions and the low and high density regions. And these regions are directly relates to the poles or the zone lines which appears on the desorption images. Okay, so one more point which I want to clear is the in the last class we discussed about the post ionization. Post ionization, it is nothing but the atoms from the lattice which are get ionized and which are near to the ionization zone at a critical distance of xc. These ions can re-ionize. Okay, so the electrons can drain out from those ions again. So this is called re-ionization, due to which you will get a different of FD images, field desorption images. As we know that the local charge state, the charge state of the ions are directly related to the electric field, local electric field in the vicinity of the tip for a given species. Correct? So here I am showing you an example of a tungsten. Fine. And this is a typical field desorption image. You can see that by plotting W3 plus, you can see that the zone lines and also the pole has a low density regions. While for the tungsten 4 plus, you can see that at near to the zone lines, these tungsten 4 plus gets accumulated. Okay, so these are nothing but a trajectory aberrations, as tungsten 4 plus needs higher potential. They have a higher evaporation field. Okay, similarly, this is the case of magnesium. This is Mg plus and this is Mg2 plus. And you can see that in between these poles, we can see there is a bright region which is appearing. These bright regions are nothing but the trajectory aberrations related to Mg2 plus ions, and it shows that due to the large curvature or higher curvature, the electric field near to the tip surface also becomes more concentrated, due to which if the local electric field reaches the evaporation field of that particular charge state ion, you will get the high density of those ions at those regions. Okay, so this is typically we can use this field desorption images to locate the poles, to get the zone lines, and also to explain the how the charge state is distributed along these low density regions. Fine. So with this I will end this class now, and in the next class what we'll discuss is we'll discuss about the pulsing methods a little bit in more detail. So as I told you in two classes before, that there are two pulsing modes, which is a voltage pulsing mode and there is a thermal pulsing mode or the laser pulsing mode. Voltage pulsing mode is nothing but you are changing the electric field at a constant voltage or at a constant temperature, but in the thermal pulse you are keeping the electric field constant, but you are increasing the temperature. Fine. So there is a HV pulsing and there is a thermal pulsing. Okay, so we'll meet in the next class on discussing on these two important points for this course. Thank you.